All right, we're going to talk about something called an adiabatic process. I know it sounds a little complicated, but trust me, it explains some really cool, everyday things you've definitely seen before. In fact, let's start right there. Have you ever been pumping up a bike tire, going at it really fast, and you touch the pump, and it's surprisingly hot? Yeah, that's not just in your head, and the science behind it is actually pretty amazing. So the whole secret lies in this idea of an adiabatic process. And here's the number one rule you have to remember. It happens fast. So fast that there's no time for heat to get into the system or for heat to escape. You know, a good way to picture it is a perfect thermos, the kind that keeps your coffee hot for ever. Anything that happens really, really quickly inside that thermos is basically an adiabatic process. Okay, so let's take that idea and go right back to our first mystery, the hot bicycle pump. So what is really going on in there to make it heat up like that? It's not just friction from you pushing the handle. No, the real magic is what's happening to the air itself. Let's just break it down. First, you push that handle down hard and fast. You're forcing all the air into a much, much smaller space. That's called compression. Now, when you squish all those little air molecules together, they don't just politely make room. No, they start bouncing off each other like crazy, like people in a mosh pit. And all of that energy, all that chaotic bouncing, generates a ton of heat. And here's the secret sauce that makes it adiabatic. Because you pumped so quickly, all that heat you just created didn't have time to escape through the metal walls of the pump. It's trapped. So the air got hotter simply because you squished it really, really fast. Okay, so we've got it. Compressing something fast makes it hot. But this is a two-way street. To see the exact opposite happen, let's take a look at a cold bottle of soda. You've absolutely seen this before. You twist the cap off a pressurized bottle, you hear that pshh. And for just a split second, you see this little puff of white mist, almost like a tiny cloud, right there in the neck of the bottle. What is that all about? Well, it's the exact reverse of the bike pump. Inside that sealed bottle, the gas is packed in under super high pressure. The second you open that cap, all that pressurized gas just explodes outward into the room where the pressure is way lower. It expands, instantly. And here's the secret to that little cloud. For the gas to expand that quickly, it has to use its own energy to do the work. Think of it like a sprinter just burning all their fuel in one quick burst. Well, spending all that energy so suddenly makes the gas get intensely cold. So cold that it instantly freezes the water vapor that was mixed in with it. And that's what you see, a tiny cloud of ice crystals. So we've seen fast compression makes things hot and fast expansion makes things cold. This all comes down to a very simple and very powerful rule that you can easily remember. And this is it. This is the whole idea in a nutshell. It's really just two sides of the same coin. On one side, you've got compression, squish something fast and it gets hotter. On the other side, expansion, let something expand fast and it gets colder. It's a direct, simple relationship. Now, you might be thinking, okay, a hot pump, a fizzy drink, that's a neat little party trick. But why does this rule actually matter in the real world? Well, let's scale this idea way, way up. I'm talking atmosphere-sized. It matters because this simple little rule is the fundamental reason clouds exist. It's not just a small-time thing. It is a massive, planet-wide weather-making engine. So let's picture the birth of a cloud. It starts with a big pocket of warm, moist air near the ground. As the wind pushes it up a mountainside, it gets higher and higher. And the higher it goes, the lower the air pressure is around it. This lets our pocket of air rapidly expand. And what happens when a gas expands really fast? Yep, it cools down, adiabatically. Eventually, it gets so cold that the invisible water vapor in it just can't stay a gas anymore. It condenses into billions of tiny liquid water droplets. And that, my friends, is exactly what a cloud is. So the big takeaway here is this really powerful connection between pressure and temperature, but only when things happen fast. Now that you know the rule, squish it fast, it gets hot. Let it expand fast, it gets cold. Start looking for it. Where else do you see it? Think about why an aerosol can feels cold after you've been spraying it for a bit, or how a diesel engine can ignite fuel without any spark plugs. This principle is absolutely everywhere once you know what you're looking for.